All right, section 5-2. This is called rational numbers. So there is a lot of vocabulary in this particular section, right? So these things that you see written here are really important to focus, pay attention, try to understand. So I'm going to go through these. These are called groups of numbers, all right? So first you have the group of natural numbers. So the smallest natural number that there is the number 1, and then what happens is it just starts to go up. So you can think of all the other numbers here that would be natural, but it would go all the way to positive infinity. So actually I would draw a sideways 8 for positive infinity. It goes all the way to positive infinity. Those are the natural numbers. So you naturally started learning your numbers at a young age. You started with, learning to count your 1, 2, 3. So that's what that is. And then whole numbers, the smallest whole number is 0. Pretty easy so far, guys. And then it just, once again, continues to rise, ... all the way to positive infinity. So as you can tell, the only difference between natural numbers and whole numbers is the number 0. Natural numbers don't have it, whole numbers do. There's only one more number there. Now we've already learned about integers. Integers start at negative infinity and come all the way down. We learned this in the last chapter. All the way down to negative 3, negative 2, negative 1, 0, 1, 2, 3, all the way to positive infinity. So that's a lot more numbers. As you can see, there's kind of a cutoff point here at negative 1, 0, right? So when you get to there, these are all the new numbers that were added. Now on the previous one, 0 was the only extra thing added. And then as you keep going down the list, you just add more numbers. So a natural number is natural. It's also in the whole numbers, and it's also an integer. All right. So as we find that out, there's multiple things. Now 0, it's only a whole number and an integer. It's not a natural number. And then if you just say negative 3, it is only an integer. It's not a whole number or a natural number. And then the last one we have here are called rational numbers. And I want to point your attention to the first 5 letters here that say ratio. And we all know that a ratio is the same as a fraction, right? And we've already been learning this year about fractions, and fractions can be turned into decimals, and we know decimals can be turned into percents. So basically what I'm showing you here is that all these numbers, fractions, decimals, percents, are all rational numbers. In other words, a rational number is any number that can be written as a ratio, which means it can be written as a fraction, which means it can be written as a decimal or a percent. So basically, guys, what we know here in rational number is anything you can think of. There's so many to list, I'm just going to name a few. 0.75, or we could say negative 0.75. Or we can say 5 1/7, or we could say negative 5 1/7. We could have negative 0.5 repeating. That would be a rational number. We could also just say 3. 3 is rational. You can write it as a fraction, 3 over 1, or 3.0. We can also say negative 10.5. All right, so I'm just listing a lot of different numbers, guys. Every number that you've ever heard in your life is a rational number. So there's no limit to the number of things that you already know so far that are rational. And then what you also know is that all the integers are also rational, which means all the whole numbers are rational, which means all the natural numbers are also rational. So every number you see on there is a rational number. All right, example 1 wants you to write each rational number as a fraction. So part A, you guys already know we do the C method, or MAD, mad, multiply, add, then divide. So I'm going to multiply 3 times 5, which is 15, and then as I keep coming around the circle, I'm going to add 2. 15 plus 2 is 17. Write that down. And then MAD, the divide part, is you divide by the same bottom number in the fraction. 3 becomes 3. So that is the answer for number 1A. Then you've got negative 3. Let's write that as a fraction, guys. Any number that is not written as a fraction, you can put it over 1, and now it is. All right, example 2 on page 235. We've got A and B. This wants you to write each decimal as a fraction or as a mixed number in simplest form. All right, so my shortcut here, there's a couple different ones, but basically what I want you to do is we're going to turn this into 0, since there's a big number out front, and 48. So we write the whole decimal out, we put that on top, and then what we're going to do is we're going to put a 1 down here at the bottom, and then as you read this, there are 2 decimal places, 1, 2. There should be 2 zeros on the bottom. So I know that gets confusing for some people trying to remember, is this tenths or is this hundredths or is this thousandths? So if there's 2 decimal places, you should have 2 zeros on the bottom of the fraction, which means that this is 48 hundredths. And then the part that we're going to do here is simplify this. Obviously the 0 you don't need, but I know that 4 goes into both of these numbers. 48 divided by 4 is 12, and 100 divided by 4 is 25. So this one is 12 over 25. Now this one, we would be at 6 and 375. Now there's 3 digits, so there should be 3 zeros with a 1 in front of it. So we have 375 thousandths. Now to simplify this, I just happen to know that 125 goes into this. So as I simplify, I again have 6, and 375 divided by 125 is 3, and 1,000 divided by 125 is 8. So that becomes your simplified mixed number or fraction in simplest form. All right, now example number 3 on page 235. I'm just going to warn you right now, it's a little bit difficult, a little bit tricky. This is definitely going into some 8th grade type of stuff. So don't feel like if you don't understand it completely that you're never going to get any of this stuff. This is just one small part of this whole section here. So this is going to sound tricky, but this is what we do. We first just give this 0.8 repeating, we give it a name, so we're calling it n. Alright, and you can kind of follow this along in the book too. So we're just saying that n is equal to 0.8 forever and ever and ever. And then what they do is they times both sides of the equation by 10. Now I don't want to confuse anybody here, alright, but it might. What we get here is 10n on this side. And what we do over here is multiplying by 10, what it does is it moves the decimal. If I multiplied by 100, it would move it over 2 spots. If I multiplied by 1,000, it would move it over 3 spots. So I'm just multiplying by 10, and what it does is move the decimal over 1 place. So now it just says 10 times n equals 8.8, repeating forever and ever. All right. And the next thing that we're going to do, and you can follow this again in your book, is we're trying to get rid of that repeating decimal. We're trying to change this thing to a fraction. And so what they do is they take n and subtract it. Well, subtracting n, which we already know from up here, subtracting n would be the same as subtracting 0.8 repeating forever and ever. All right, so what you'll see here is it's kind of an interesting way to solve this. 10n minus 1n is now 9n. And then on this side, when you subtract 0.8 repeating, right, all of these end up canceling out, and crazy enough just equals 8. So what happens is now we have 9n equals 8. How do I get n by itself? I divide by 9. So as you can see here, it now says that n equals 8/9. So it's kind of weird, but the reason we started this out by multiplying by 10 is because we only needed to move the digit one place to the right. If there's another number that repeats after 2 places, we would multiply by 100. If we needed to move the decimal 3 places, we'd multiply by 1,000. Again, that's kind of tricky. Don't feel like you have to understand that completely, but if you follow those steps, you will be able to get any of those correct. All right, another concept here on page 236 is this term of irrational. All right, so what we have is some numbers are irrational and some numbers are rational. So we already know what the rational numbers are. Those are numbers that can be written as a fraction, a decimal, a percent, a whole number, an integer. All of those, negative or positive, are rational. And what you know in a rational number, let's just have an example here, is you always know what the next digit is, and the next digit, and the next digit, and the next digit. You know what every one is. You don't have to look it up, solve anything. If this is 0.3 repeating, I know the next one is a 3, and a 3, and a 3 that goes on forever. An irrational number is like you see down here in the example, or at the top of the page. It says 4.23, 223, 2, 2, 2, 3. That's just an example that they have. Now it looks like it has a pattern, right? It goes 2, 3, and then it goes 2, 2, 3, and then it goes 2, 2, 2, 3. So you would think the next one would be 2, 2, 2, 2, 3. And it might be, but the problem is this is not a repeating pattern. We don't know for sure that the next number would be a 2, right? So basically what happens here is this number goes forever, dot, dot, dot. It's irrational because I don't really know that next digit. It's one of those. Now, you also know another irrational number. You've known this for quite some time. It's the number pi. Pi is actually a Greek letter. But it goes 3.141592654, dot, dot, dot. Now, it goes on forever. And I know that you can Google search this number and it'll probably give you what pi is. It'll tell you every digit forever. I honestly don't even know how they got all those numbers. I've never looked into it that far. But here's what I know. There's no repeating pattern here. So I have no idea what the next digit is unless I Google it. That's not really a way to solve this here. So that is also a rational, that is also an irrational number. So we just want to know irrational numbers are numbers that go on forever and do not have a repeating pattern. Rational numbers are the numbers that do go on forever and there is a repeating pattern. You either know it's 3's forever, or if it's a terminating decimal, it has 0's forever. So there you go. All right, that's the big difference between the two sides. All right, in example 4, it says to identify all sets to which each number belongs. The first one we have is -6. Guys, we remember that from, back in the video. -6 is an integer. It's not a natural number. It's not a whole number, but it is an integer, which means it is also a rational number. So -6 fits into the category of being an integer, and it's also a rational number. Part B, 2 4/5. Now, it's not a natural number, a whole number, and it's definitely not an integer, because all of those numbers go 0.0. This is just a rational number. Rational number is a ratio number, so that means it can be written in the form of a ratio, which means it's a fraction or a decimal, because decimals and fractions are ratios. And then the last one we have here is this number that goes on forever. You should notice that there is no repeating pattern. You might see the 4-1, 4-1-1, 4-1-1-1, so it looks like it has a pattern, but that doesn't mean it's a repeating pattern. So what we do is call that an irrational number. All right, so that's the end of the video, guys. Best of luck on this. It shouldn't be too difficult.